So in this last video for our Exam 2 preview for Calculus 2, we're going to talk about application problems of these integrals. We're going to start with number 13, which has to do with what we call Hooke's law. And Hooke's law is the ability for us to determine the amount of force that a spring can apply based on its spring constant and its position where the spring is at. So if you've got a spring that's in equilibrium in this shape, if we were to compress it a certain distance, the distance that it's compressed or position that it's compressed to multiplied by the spring rate can allow us to calculate the amount of force that was needed to compress that spring and therefore how much force the spring is pushing back on us. Now if we extend this just a little bit farther and take the amount of force that's applied at any given position and multiply it by a distance that it's being moved, well, force times distance ends up calculating what we call work. And so we can start to answer some questions when we introduce this integral now. If we have 60 newtons of force that's required to stretch and hold a spring this distance from its equilibrium position, the constant value ends up computing out to be 600 newtons per meter. So our question becomes how much additional work is needed. So this is our cue that we're talking about an integral here. How much work is needed or required to stretch the spring an additional 0.2 meters if it's already been stretched 0.1 meters from its equilibrium. Well, as far as the setup goes, we'll say something like this. The work is equal to our starting position, 0.1, and we're going an additional 0.2 meters away, so 0.3 is the result that we'll use here. And we'll integrate from negative 600 times x with respect to x. Now I'm using my calculator off screen, and that computes out to be negative 24. Now here again, since we took force, which was a measurement in Newton units, times a distance, which is meters, one might call this a Newton times meter unit. As we'll see later in our physics class, we'll actually call that the energy of work for joule, or as joule. So negative 24 joules. Now you might be surprised to see that as a negative 24, but let's just remind ourselves here of what's happening. This spring, when sitting at rest, is in its equilibrium state. If I start pulling it 0.1 meters and then an additional, let's see, if I pull it 0.1 meters and an additional 0.2 meters, I'm stretching the spring back. Its tendency is wanting to fight that and return back to equilibrium. So the work that it can do, or that it's doing, is, we can consider that as a negative number because of the opposing forces. But it really just does matter on or depend upon your perspective. By changing our point of reference, we might report this as a positive 24 if we think about the perspective in which we're applying the math. But in this case, I'm happy to see negative 24 as the result. Now in the final example here, we need to find the hydrostatic force behind the water that's pushing up against this wall of a dam. Now the force that we use to compute that is given to us in a formula such as this, where we integrate from A to B, where A is the lowest point on the dam wall and B is the highest point. We're going to take the density of the liquid, which we call rho, times our gravitational constant, times the height of the water, which is going to be some upper boundary height minus y. Now a lot of times that height ends up being our b value here, but we'll discuss that here in a moment. And multiply that by the width of the dam based on its height position. And we'll integrate that with respect to y. So I tend to believe that the hardest part of this problem is determining our width function. The rest of the information is usually given to us pretty clearly, but determining the width function is kind of difficult. And there's a hint that's provided to us here. To find the width function, a lot of times what we do is we place the origin at the center of the base of the dam, and the y-axis is going to be this vertical direction, and our job would be to find the equation that represents this right side edge. Now right now we're dealing with a trapezoidal face, so this right side edge is linear. But it's entirely possible if the dam itself was quadratic in shape. We might have a quadratic equation here, or if it was any other equation for that matter, we can investigate it that way too. But this is a linear equation, so we'll go ahead and establish that first. So I'm going to note that this position here, if our origin is right at the center, well, that's 17 units to the right and 0 units up. And then this position here, well, that's half of 68, so that's going to be 34 units to the right. And this note is telling me that it's 51 units in the air. So now I have two coordinates. I can establish the equation between those two. A quick calculation of slope indicates that the difference in the y's and the difference in the x's produces 51/17. And then we can use our point slope formula by choosing just one y value and the slope. So we'll go with 51/17 times x minus the associated x value, minus 17. This to me looks like the equation for this wall face is y equals 51/17 times x minus 17. If we distribute, then what's that become? 51/17 x minus 51. So we've got a nice equation that represents the wall of the dam. We do have a problem, however, and this is what makes this step a little bit challenging. This equation is built on the variable x, and based on our description over here, we actually want a width based on y. So let's take just a couple moments and isolate x here. And so if we add 51 to both sides and divide by 51/17 or multiply by 17/51, we get an equation that looks like this, where our x coordinate is the result of this computation. And we do also have to be careful that this x coordinate represents the measurement or the horizontal distance from center line. We're worried about the entire width of the dam here, so we should really double this. And so our width based on y is going to be 2 times 17 divided by 51y plus 17, or 34/51y plus 17. Okay, so all of that preliminary work done just to find the width measurement of the dam wall based on the height position, now we can fairly easily compute the force behind the wall. Now, in this example, we are assuming that the water level is at the top of the dam, so the height of the dam here extends from 0 up to 51. We have a rho value of 1,000 kilograms per meter cubed, times an acceleration on Earth of 9.8 or 9.81 meters per second squared, multiplied by the height of the water minus y. Now the water level is at 51, so we'll use 51 minus y, and we'll multiply that by the width of the wall at any given point. We'll call that 34/51y plus 17, and we'll integrate all of this with respect to y. Since we have the equation set up and we have the calculator available, I'll let it do the math for us. And actually I need to be a little bit more careful here. This should be a 34, and this should be a 34 as well, because we are multiplying the entire function here by 2. So 2 times 17, this has to distribute to both terms. Now again, using the calculator, I end up with the result 578.358360. So that is quite a lot of force. And this is measured in newtons. If we were worried about significant figures, well, this is kind of a limiting factor here, but usually 3 or 4 significant figures would be appropriate. We might report this as 5.78 times 10 to the 3/6/8 power newtons. So quite a lot of force behind a dam that's holding that much water. It's rather large. Okay, well, I hope that these two examples help clarify the issues that we're seeing in class right now. Again, the majority of our focus has been on different integration techniques and setting them up and allowing the calculator to do the work for us. But these two examples here are nice to revisit because they do show us some applications of the work. If you have further questions, please let me know. Thanks for watching.